For the purposes of this talk, imagine you're a web program, and you're writing the server-side code for a web application. It needs to generate a page of information like this. And the page has several different regions containing different information. And in order to generate the information for those regions, we're going to have to fetch data from multiple different data sources. So these might be databases, they might be caching services, or other back-end services in your application. So in order to do this efficiently, we're going to have to do concurrent access to multiple data sources when we're fetching data from several different sources. We want to do it at the same time to reduce the latency. If we're fetching multiple data items from the same source, we'd like to be able to batch those requests together so that we're doing fewer round trips and making better use of the network. And if we need to fetch the same item of data from multiple places in the page, we would like to not fetch that data multiple times. So we need some form of caching or deduplication. So you could just do this in a brute force way. You could do all of your data fetching right at the start of your application, and you could make sure that you're getting the concurrency right and the batching right. But the problem with this is that it destroys the modularity, right? So you might like the code for the different regions on the page, there are different modules in the source code. But if you did all the data fetching up front, every time we need to do more data fetching, we're going to have to modify this single place in the code base. But it's worse than that. You might have data fetching that depends on the results of other data fetching, which would require you to mix up the business logic of the data fetching in your application. So it's not always the case that you can extract all the data fetching out to the front. So you probably think, well, we probably ought to use some concurrency, and that's usually the way this is done. So let's imagine we've got some kind of concurrency that lets us do the batching that we need to do. And we fork all of these regions in separate threads. But that's not ideal because explicit concurrency still relies on the programmer to get the concurrency right. You can still introduce false dependencies. You can forget to fork, so you don't have enough concurrency. So the programmer is too involved in getting this right. So it's worth reflecting on why we have explicit concurrency. So explicit concurrency arises because concurrency gives us non-determinism, right? So, and we need to be able to say that we want non-determinism in the program. But in this case, we're only fetching data from data sources, so the programmer doesn't really care about the order in which they fetch the data, they just want it to happen efficiently. So the fact that it's non-deterministic is not really an issue, the programmer doesn't really care. So perhaps we want something more implicit. So let me talk about one more example. This is closer to the example that we're using at Facebook. So a rule engine is a service where the code that's running inside the service is a set of rules comprising some business logic. And the job of the service is to take some input parameters, evaluate each of these rules using some data fetched from back-end data sources, and to return the results of those rules. So this is rather like the web application example, except that the unit of modularity is now much smaller, right? The unit of modularity is a single rule. So it's unthinkable that we could extract all of the data fetching and do it up front. Furthermore, it's unthinkable that we could do any kind of explicit concurrency here. Here's a fragment of code from our DSL that we're working on at Facebook. So this fragment computes the number of friends in common between two Facebook users, X and Y. And the primitive data fetching operation is this friends of function. So friends of takes a Facebook user and it returns the set of friends of that user. So we have two calls to friends of on X and friends of on Y. And we take the intersection of those two sets and then finally compute the size of that. And that gives us the number of Facebook users in common between these two friend sets. So this illustrates that even though we have two separate friends of calls, what we really want to do is to have those two requests, because they're requests to another backend service, have those two requests collected together and batched and executed as a single request. And we'd like to do that without sacrificing this nice, functional, expressive language that we've got here. So the abstraction that I'm going to describe in this talk gives us that. It gives us a nice, concise, modular, expressive concurrency model. And executes efficiently. So it batches all the requests and executes concurrently. So I'm going to show you first of all a concrete example of what it looks like to program with this programming model, and then I'll talk about the implementation. So the concrete example, I'm going back to the first example, the web application, and I'm going to use a blog as the example. So our blog will look like this. We've got 3 different panes on the page. The main pane will will show a set of posts, blog posts. And on the left, we've got 2 sub-panes. The top one's going to show the most popular posts, and the bottom pane on the left will show the topics, post counts organised by topic. All right? So I'll do this top down. So the topmost function in the code is this blog function. So blog, you can see, returns some HTML, and it returns some HTML in a monad called fetch. So fetch is the abstraction I'm describing here. Fetch lets you do some data fetching, and its implementation will provide concurrency. So in the implementation of blog, we're composing 2 panes, the left-hand pane and the right-hand pane. So those are also fetch operations, and they return some HTML. And here I'm using the applicative combinators to combine those 2 together. So applicative is quite important, as we'll see. And given the results of those 2, we can combine them and render the page using the render page function. So the left pane, which I'll say no more about in this talk, you can see the paper for the code for that. But the left pane is composed of the 2 sub-panes on the left, popular posts and the topics, and we've got some more render functions. So I'm going to go into more detail about what happens on the main pane, but before I do that, we need to talk about some data types, which comprise a data model for our program, and how we fetch the data from the fetch monad. So we need a post ID, which identifies a post, and some post content. So for now, these are abstract types. And we need some metadata about the post. So the metadata is the post ID, and it's the date the post was created, and possibly more stuff. And there are 3 data fetching operations. So we can get the post IDs, which is the complete list of IDs of posts in the blog. We can get the post info for any given post ID, and returns the metadata for that post. And we can get the content for any given post. So these are the 3 primitives at this level of the programming model. They're actually implemented in terms of a single primitive in the framework. And you can see in the paper for more details about that. So here's a function written using this programming model. So this one gets all of the metadata for all of the posts in the blog. It's called getAllPostInfo. And so it's just 2 lines. The first line is get post IDs. So it gets all the post IDs for all the posts in the blog. And then maps get post info over those IDs. So for each of the IDs for a post, we're going to get the metadata. So it's just basic monadic programming here. There's nothing complicated. So here's the code for the main pane. So what do we do? Well, first of all, we're going to get all the metadata for all the posts. That's a function I showed on the previous slide. And then we're going to sort those by date. So with the most recent first, and then take the first 5. Those are the 5 we're going to display in this pane. And then we'll get the post content for each of those posts. So here's an example of some data that depends on previous data. All right? It would have been hard to extract this and do it at the start of the program, because we don't know which posts we're going to need the content for until we've sorted them. Okay, so we've got the content for all the posts that we're going to display, and finally we can render it. So you're probably looking at this and thinking, where's the concurrency? All right, it doesn't look like there's any concurrency there. And the concurrency is implicit in the structure of the code. Right, you don't have to use any specific concurrency functions or tools. You just use monad and applicative and the tools that you're used to. And at the same time, there's no concurrency bugs, right? Because you haven't had to say anything about the concurrency, so you don't have the opportunity to get it wrong. So there's also no manual batching. So going back to this function I described earlier on, get all post info. Look at the last line. So it's mapping get post info over a set of IDs. And naively, you might expect that's going to make multiple requests to the database. So without any batching, if our database is a SQL database, it might do select, 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 select. But what we really want to do, and what the framework will allow us to do, is to batch all these requests together into a single SQL query that fetches them all together. So given a suitable SQL backend for the framework, we can do this batching. So let's talk about the implementation. So fetch is going to be a concurrency monad, and it will work in a series of cycles. So in each cycle, we run the computation as much as possible so that we can collect all the data fetches that need to happen. And then we'll fetch all the data using concurrency, using batching as much as we can. And then go back to 1. And that cycle repeats until the computation is complete and we fetch all the data and we have the final result. So we need a result type for our monad. So this is the result type here. And it might look familiar to you if you've seen concurrency monads before. There are 2 constructors. There's a done constructor, which is the final result. If the computation completed without needing any data, then it returns done. Or it was blocked. And the block constructor has 2 fields. It has a sequence of blocked requests. So this is the case where the computation is blocked on multiple things, and this sequence of blocked requests are the set of things it was blocked on. And it has a fetch A, which is the continuation to run after we fetch all the data. So the idea is that the surrounding loop is going to fetch all the data for those requests and then execute the continuation, which will continue the computation. So we wrap the whole thing in this fetch type, and fetch is actually an I/O. We're threading I/O through our computation. That's just to make some things easier when we're fetching data. You can actually do it without the I/O. But this doesn't lose any safety because we don't expose the I/O to the user. So the instance of a monad is fairly straightforward. So return just returns a done. And in the case of bind, what we need to do is execute the left-hand side and then take a look at its result. If it was done, then we can go ahead and do the right-hand side. If it was blocked, then the whole thing is blocked. And the continuation, in the case of the blocked, is, well, we've got the left-hand side, and we need to just bind the right-hand side. Right, so this is very similar to a free monad, the free monad construction. So all of the magic happens in the applicative instance. So in the applicative instance, unlike in the monadic bind, we can run both sides of the applicative app operator, this angle bracket style. So the left-hand side is the function, the right-hand side is the argument, and we can run both of those here in the I/O monad, and then look at both of those results. If they were both done, then we can continue. If one of them was blocked, then all we have to do is to construct the appropriate continuation and return the blocked. So that's the next 2 cases. And in the final case, this is when both sides of this composition got blocked, then we have 2 sets of blocked requests, one from the left, BL1, one from the right. And we combine those 2 sets together to give us the set BL1, and this is the append operation, BL1, BL2, and the final continuation is just the continuation from the left applied to the continuation from the right. So this is how we are sort of propagating sets of blocked requests up the tree of the computation. So given this, mapm becomes automatically concurrent. It is provided that we're using mapm that's implemented by Traverse rather than the default implementation of mapm which uses monad. And I believe that this change is going to happen in Haskell now that we've moved to applicative being a superclass of monad. So with Traverse being the implementation of mapm, Traverse expands into a sequence of applicative operations, and that means that when we call mapm in the last line of getAllPostInfo here, that's expanding into a sequence of applicative operations that all get batched up together. So we collect all of those data fetches, and that's how we can batch them together. So putting this together, let's just look at what happens at the outside of the monad. So we need a way to fetch all the data. So I'm just abstracting over that for now in the function fetch, which takes a list of blocked requests, and its job is to fetch all the data. So given fetch, we can just have a simple recursive loop that takes the fetch computation, runs the computation in the I/O monad. If it's done, then we're done. If it's blocked, then we call fetch on all of those blocked requests. And then it recursively calls run fetch to continue the computation, passing the continuation that we got from the blocked value. Right, so if you imagine this running this is showing you the dependency tree of data fetches. So the dependency tree is constructed by the app operators, which give you a branch. So app branches the tree into two, and dependencies arise from the monadic bind. So every time you say monadic bind, if you don't have the value on the left, you can't compute the value on the right. So this is how a dependency in the tree arises. So when the run fetch loop runs for the first time, it's going to get this set of data fetches, and it will perform those and maps them concurrently. And when the results of all those are available, we can do the next round of data fetching, which will be this round. So you can see that the tree is explored in layers. So we execute one layer at a time until the tree is completely explored. So, but you might think, well, do I really need to write my program in this applicative style? Maybe I don't like it very much. And the idea is that given that the programmer doesn't care about the order of the operations, we can automatically translate the do notation into the applicative style. So given that the two do statements here in this example don't depend on each other, the programmer doesn't care which order we do them in, so we can batch them together and translate this into the applicative version, which will execute concurrently. So our idea is to implement this transformation in the compiler in a way that you have to explicitly say when you want the transformation, because it might not be the case that for all monads this is actually valid, because it relies on the definition of applicative doing the right thing, being equivalent as far as the programmer is concerned. Okay, so we imagine having a flag that you say to the compiler, I really want this transformation to happen on this particular piece of code. So I mentioned right at the start of the talk that we want to do caching. So if the same piece of data is fetched in multiple parts of the computation, we ought to return the same result. And that's useful for consistency. So if you're rendering a web page and the data changes behind your back, you really like it that the page is showing consistent information in different parts of the page. So caching helps you do that, and it also helps you avoid fetching data multiple times. So all we have to do is pass around a data cache in the monad, and the data cache remembers all the data fetches that we've done and lets you return a result if you've seen it previously. So having done this, it gives you a really nice way of replaying computations, because the cache at the end of the computation has collected all of the data that you fetched. So you have a complete record of all the data that was fetched, and you can use that to replay the computation, even though the data might have changed while you were, or between the time that you originally ran it and the time that you ran it again. So this turned out to be really useful for profiling and debugging and testing. So the reason I developed this idea was that we're doing this project at Facebook called the Haxel project, and it's a rule engine that's been used for detecting spam, detecting phishing, all kinds of bad content that might happen on Facebook. So the service embodies a large set of rules, and currently these rules are written in an in-house language called FXL, and we're translating all of that into Haskell using our fetch monad. So, and we have many different data sources corresponding to different backend services at Facebook. And because the rule engine needs to change the rules many times per day in order to respond to new spam attacks, we have to be able to hot swap in the new code every time the rules change. So we've developed a way to compile new code, distribute it to all the machines, and load that in and have it start running. So the current status is that we've implemented all the functionality that we need for this application, and right now we're testing it against real workloads and doing performance analysis, fixing performance bugs and fixing correctness bugs as well. You can see the core framework, which we've open sourced. You can go to github.com/Facebook/Haxel, and the code for the core framework is there and you can use it. You have to implement your own back-end data sources, so it's a framework independent of the data sources which you can implement yourself. So just to conclude, I'd like to compare what we've done to implicit parallelism. So the problem with implicit parallelism is that it's hard to find the right kind of granularity if you're trying to exploit all the parallelism that's inherent in functional programming. But data fetching doesn't really suffer from that problem. Okay, so a data fetch is much more expensive typically than a small computation. So exploiting all of the concurrency inherent in a pure expression with data fetching tends to be worthwhile. So it's like implicit parallelism, but just for data fetching. And so the program is just using familiar tools. They're just using monad, applicative, and they don't have to learn any new concurrency constructs. So in the future, what we'd like to do, so you saw that the scheduler runs the computation in layers, and it may be that some of those data fetches in one of those layers are much more expensive than some of the others. So there might be a more efficient way to do the scheduling than running everything in layers. We might be able to continue parts of the computation that the data fetching has already completed for. So we'd like to be able to do more flexible scheduling and trade off batching for latency. That's the end. I'd be happy to take questions.
Thanks, Simon. That was a very nice talk. Concise from Chalmers here. So, can you show the definition of bind for the fetch monad again?
Sure.
So it seemed to be linear in the depth of the nesting of block requests. Is that true?
Which part is linear?
So if you have this, if the left computation does a lot of nested block requests until it finally is done, then the bind is going to be linear in that it's going to traverse all of that until it finds it done, right?
Right.
So that means if you, it has the same problem as list append, which is linear in its left argument. And so if you append something at the end of a computation using bind, it's going to be linear in the sort of number of fetches that computation is doing.
I don't think so. So are you referring to this append here? So where we
no, just the bind, just the code for bind.
Just the bind.
So the typical thing is to fix it with a continuation monad, or to make a commercial for the last talk in the Haskell Symposium on Friday. There's another solution for it, but you haven't. So if you use left recursion, then it's going to be quadratic behavior. So if you have a performance problem, then this might be it.
Well, so what happens if you get a block sort of deep in the computation as the block bubbles up to the top, and it builds this continuation? So I think it's maybe linear in the depth, but that's not usually a problem, I think.
Maybe we can take a look back.
Yeah. Okay.
Lars Hubel from Munich. My question is about this implicit parallelism, which you get by specifying the applicative in a slightly different style than the monad. My question is twofold. So the first part is, have you, in your real-world experience with this project, experienced that you got accidental sequentialism versus parallelism, where some programmer forgot to enable this rewriting of do notation into a more applicative style? And the second part is, would you think it is actually feasible to mandate that if you want parallelism, that you should use a new type wrapper around your fetch monad, like par fetch?
Okay, so the first part of the question. Right now, we are not doing this transformation, so I've still to get any real-world experience with doing that. What we are doing is translating our old language into the new language with applicative. And our experience with that is that we get enough parallelism. We're essentially doing the transformation at the same time as we translate the old language into the new language. So, and we're getting perfectly acceptable results as far as concurrency goes. So remind me about the second part of the question again?
The second part is that if, should you get these kind of accidental, that you get parallelism when you actually want sequentialism, or the other way around,
right?
If you've investigated whether to mandate one behavior with the other with a new type wrapper around the monad.
So the time that you might want to do this is when you have real side effects. So if you want to incorporate writes into your language of data fetches, then you probably really do want to say something about the ordering of the data fetches. So in that case, you want to disable various things. You want to disable the automatic translation of do. You want to probably disable caching, because you might have changed something that's been cached. So this is still something we want to explore. Right now what we're doing is we sometimes do writes, but we limit it to either writes or reads within a single run fetch. but perhaps you're right. Perhaps you need a separate monad as well.
Okay, thanks.
And I think with that we've run out of time for questions. So I guess. So our next speaker is Jeremy Gibbons, and he's talking about folding domain-specific languages, deep and shallow embeddings.